Thank you, Karl-Heinz, and thanks to the organizers for inviting me. I've been asked to talk about the SKA, and I thought I'd try and make some kind of connection to particle physicists, but not much. I'll start off talking about the dark universe with a little bit of particle physics reference, and then I will say something about the SKA, which, as you probably know, is the most exciting and biggest ever science experiment in Africa. So if I start off with dark matter, which clearly is a subject close to some of the talks in this conference. As you probably know, the first evidence for dark matter was the behavior of galaxies, the dynamics of galaxies. And it was discovered many decades ago that the velocity of stars in spiral galaxies was too large relative to the amount of baryonic matter that was contained within the galaxies. And so this led to the necessity, failing any other kind of explanation, for some kind of dark matter which was non-baryonic. Not just a small amount, but at the level typically of 80%. In other words, dominating the galaxies. And so for a long time, our standard model of cosmology is based on the assumption that we need a cold form of dark matter, typically assumed to be a particle, something like a weakly interacting massive WIMP, in order to stabilize galaxies. But actually, the second piece of evidence for dark matter is just as strong, and sometimes you could say stronger, coming from looking back at the history of the universe and calculating how many galaxies could have grown to up to today, 14 billion years later. You realize that it's impossible to have the current distribution of galaxies without an amount of cold dark matter that is roughly the same order of magnitude, 80% dominant over baryonic matter. So the most common model for CDM is a particle dark matter, and there are various experiments looking for that, and I believe you'll have a talk on that. There's just one example there, the xenon experiments, about which I know much less than all of you do, but it's a nice photograph. Now, in addition to dark matter, we have another dark component in the universe known as dark energy. And the simple idea of what it is as follows. Galaxies are moving apart from each other in the expanding universe. The space is expanding, according to Einstein's theory and measurements of redshifts of galaxies. But in the course of that expansion, galaxies are forming, growing. The number of galaxies is mounting. The distribution of galaxies is getting more and more dense, and what would be if the universe were not expanding. And the gravitational attraction between galaxies is slowing down the expansion of the universe. But from the late 1990s onwards, it became clear by measurements of supernovae, about which you probably also have heard or will hear in this conference. Measurements of the redshifts of supernovae showed that the universe actually was expanding faster and faster over about the last 5 billion years of its 14 billion year history. So this was a surprise. It wasn't predicted, it wasn't expected, but it's by now very well confirmed that within our standard model with cold dark matter and Einstein's theory of general relativity, the universe appears to be accelerating. And the simplest model to explain that is that the vacuum energy, the energy of the vacuum, adding up all the energy of the fields in the universe, which effectively has a negative pressure because it's a Lorentz invariant, so its energy density plus its pressure is zero in Einstein's theory, that this has a effective anti-gravity effect countering the gravitational effect of galaxies. And Einstein's equations verify that this is exactly what dark energy in the form of a vacuum energy will do. It will accelerate the expansion, and it will only happen late in the universe because if the dark energy is sufficiently weak, sufficiently low level. And this seems to explain the universe very well. We have a 6-parameter standard model which is consistent with all observations up to now. But that does hide a number of issues, one or two of which I'll touch on. So we have this current energy budget of the universe. The dark energy is dominant at the level of about 70%. This is the stuff that accelerates the universe. Is it the vacuum energy? Is it some kind of field? We don't know. The dark matter dominating over baryonic matter makes up the rest, and this builds and stabilizes galaxies, and baryonic matter makes up the galaxies and the people who observe this whole process. So this model of dark energy, this nice simple model of dark energy, has one fundamental and devastating flaw, and that is the following, that the observed value of the vacuum energy is at the level of milli-electron volts. That's the energy scale. That's what we need to understand the universe about us. But the prediction is that the vacuum energy is either zero if there's supersymmetric cancellation, but we know the universe is not supersymmetric for most of its history, so it seems pretty unlikely unless there's another way to get lambda zero, or lambda is at least 10 to the 12 electron volts to the 4 if we use the lower limits at the TeV that's being probed by CERN. So the attempts to explain either why lambda is zero and there's something else that's accelerating in the universe, or to account for this unbelievably tiny 10 milli-electron volt energy scale, have been going on for decades, 2 decades, and probably the most commonly known attempt to answer this small value of lambda is through the multiverse, the idea that there are of order 10 to the 500 vacuum energy states at different lambda levels in a collection of separated universes called the multiverse. It sounds a little bit epicyclic and many people don't actually buy it, but that's about as far as we've got trying to explain this. But I'm not going to go further into that. That's a kind of quantum gravity particle physics issue, which I won't be able to say more about. What we would do as cosmologists, as opposed to particle physicists, is we can do consistency checks for dark energy, dark matter, and indeed Einstein's theory of general relativity. Because it may be that we're interpreting dark matter and dark energy within the framework of Einstein's theory. That theory itself may need modification on the larger scales. So how do we probe dark matter, dark energy, and GR on cosmic scales? We can probe dark matter, of course, in terrestrial laboratories. We can't probe dark energy except for some exotic models in the same way. But I'm talking about probing dark matter and the other two things that we can't probe on Earth alone on the largest cosmic scales, because these phenomena that I'm talking about govern the very large-scale behavior of the universe. So in order to get the statistical power that will allow us to actually start really discriminating between different theories of the dark sector and of gravity, we need to measure the characteristics of not just millions but billions of galaxies. And by measuring the positions, which give us the correlation properties of galaxies, the correlation function, which contains our archaeological smoking gun signatures of the early universe, for example, but also it contains characteristic features of the amount of dark matter and the amount of dark energy. And also by measuring the shapes of galaxies, millions and billions of galaxies, you can have a more direct probe on the dark matter. Doing those things together, you can hope for predicted sub-percent constraints on the amount of dark matter and dark energy in the universe, and on various properties of those parts of the dark sector, as well as very tight constraints on whether Einstein's theory is actually governing the ultra-large scale behavior of the universe. The other dark sector, which I've just mentioned now once and not go back to, is, of course, the neutrinos. The neutrinos are also dark matter particles because they're weakly interacting. They are ultra-relativistic at the time that the cosmic microwave background is released, soon after the Big Bang, the beginning of the universe. But they have become relativistic depending on what precisely their mass could be. By now, they are non-relativistic, so they are a form of dark matter which is warm at the moment, as opposed to cold. The constraints from galaxy surveys, together with the cosmic microwave background, already put the sum of the neutrino masses at less than 0.3 electron volts. And that's set to improve in the next 10 years with future galaxy surveys and future CMB surveys by an order of magnitude to the order of 10 milli-electron volts. So it's competitive with at least maybe currently beating the terrestrial constraints and competitive possibly with future constraints. So now let's switch gear and just talk about the SKA. Why radio telescopes connected to all of this? Well, one of the features of radio telescopes, not as opposed to, but something that they're slightly better than optical telescopes with, is that they can cover the largest ever volumes of the universe. They can measure the positions and in the future the shapes of the largest number of galaxies. Let me say a little bit more about radio telescopes. What are we actually looking for? Well, this is not the only radio signal, but I won't have time to give you the other radio signals that we can use to pick up galaxies, but this is the most important one from the point of view of my talk, and that is the 21 centimeter emission of hydrogen due to the spin-flip transition. It's a forbidden transition, but hydrogen is the most abundant baryonic element in the universe, and so there are a lot of hydrogen atoms emitting at a very low rate, but there's a lot of 21 centimeter emission going on throughout the history of the universe from 400,000 years onwards, which is the time at which neutral hydrogen first formed. So this is a neutral hydrogen emission. And, sorry, not that one. This hydrogen gas is invisible, obviously, in the optical, but it's shining in the radio. And I'll show you here an example of a single galaxy on the left, the optical image showing the shining stars, the baryonic image of the galaxy, and on the right, a false color-coded, according to the strength of the emission, image of the 21 centimeter emission from that galaxy. And you can see that the galaxy is a lot larger. The hydrogen extends a lot further than the stellar component in some galaxies. So we can also see huge clouds of hydrogen in the epoch of the universe called the Dark Ages. After the formation of neutral hydrogen, the universe consisted, in baryonic terms, mainly of hydrogen with a little bit of helium, neutral helium, and there were no stars. So the universe was in what we call the Dark Ages. And these clouds potentially in the future, not in the first phase of SKA, but the second phase, will be mapped by radio telescopes, possibly on the moon, on the dark side of the moon, because it's at very, very low frequencies, very high redshift. So the cosmic dawn that lights up the universe to end the Dark Ages, when the first stars form, from that moment onwards, the hydrogen rapidly becomes ionized and neutral hydrogen is left only trapped within galaxies. So here's a cartoon of the history of the universe. We don't know about the beginning, quantum gravity. We don't have the theory that can explain the beginning of the universe, but if we assume there was a big bang, the singularity being regulated by some quantum gravity, a period of rapid superacceleration called inflation, which produces the hot plasma in the big bang of the universe, and then the universe decelerates and accelerates off during the last 5 billion years at a very much lower level, milli-electron volt, as opposed to sort of many, many TeV and above in inflation. And here we have the hot plasma cooling, and then eventually hydrogen is able to capture electrons so that neutral hydrogen forms. There's the Dark Ages when there are no stars. The first stars light up in the cosmic dawn, and those stars then accumulate into galaxies, which cluster together to form clusters of galaxies, and we have this cosmic web of large-scale structure, which is driven by the amount of dark matter and also which is opposed by the amount of dark energy, which obviously suppresses the growth of that structure. Now here's another cartoon which is a little bit more from a slightly more logarithmic scale. Here's that plasma. There's the cosmic microwave background released when the decoupling of photons and electrons takes place. There's the neutral hydrogen. There's the reionization period and the end of reionization period when all the neutral hydrogen is trapped in galaxies. So radio telescopes can, in the future, will be able to map the Dark Ages. In the near future, we'll be mapping the epoch of reionization, and we'll also be mapping neutral hydrogen in the galaxies. And so we have access to huge volumes of the universe, whereas optical telescopes have a much lower redshift or backward in time reach, and typically a lower sky area as well. Right, so the SKA is the premier radio telescope. Current radio telescopes are not able to do these kind of cosmological things. They're only able to track individual objects and tell us a little bit about classes of objects. But the square kilometer array in phase 1, which should be about 2025 onwards, and you can add in as many years as you're used to adding to the timelines of any big experiment. It's probably going to be a bit later than that. In phase 1, the SKA comes in 2 versions. SKA mid, the mid-frequency array, which is made of dishes of approximately 15 meters diameter. And the low, which is dipole antennas stuck in the ground. These things come in hundreds of thousands, and these things come in hundreds, because they're obviously much higher tech. But this is the low-frequency stuff that measures the epoch of reionization. So the mid will be in South Africa. It's already 1/3 built, and I'll come to that in a second. And the low will be in Australia, the western desert of Australia, both very low density areas where there's no mobile phone signals and very little radio frequency interference. SKA phase 2, which is coming from a 2030 earliest onwards, that'll be approximately 10 times the size of SKA1. And that will, in South Africa, it will also branch into Africa, forming spiral arms of these dishes to improve the resolution for individual objects. So here is a map. The Australian SKA low is around about there, and the South African one is in the Karoo near Carnarvon, showing phase 1. Here's the actual astronomy advantage geographical area, which is protected by an act of parliament from any developments that could interfere with the construction of the SKA. And as I mentioned Africa, you can just see the list of partner countries in SKA Africa. Currently, an obsolete telecommunications dish, I think it's 30 meters diameter, has been converted for radio astronomy by astronomers and engineers from South Africa and from Britain, and people in Ghana have been trained to start operating this telescope, and science will be done with that telescope, and eventually this will be replaced by outriggers in SKA phase 2, and outrigger dishes also in the other countries of this amazing collaboration, which, as I say, is the biggest ever science experiment built in Africa, and is a major boost for the future of science on this continent. So MeerKAT is the precursor to the SKA, and it's South Africa's own 64-dish mid-frequency array. It belongs to South Africa until the SKA phase 1 clicks in, and then it is absorbed into SKA1. So for the next 5 years or so, we have this, what we could call as the world's best radio telescope array in the mid-frequency. This is an actual dish. I think that was amongst the first that were put up. The construction was completed in late 2018, and science operations started last year, and they're kicking in. I mean, it takes 2 to 3 years to get science operations up to full capacity, and we're in that phase at the moment, but already amazing science is being produced by MeerKAT, South Africa's array. We don't mind if SKA1 is a little bit late, because then we have the array for a bit longer to ourselves, but obviously we want SKA to come. Here's some photographs during the construction phase. You can see from an airplane where the dishes are. This is the warehouse where the dishes are manufactured on site, and it's a major, the civil engineering to stabilize this thing with concrete and so on is in itself a major operation. And here is the underground facility containing the massive supercomputer. That's the most powerful computer in Africa, underground to shield the radio interference that it would generate. So this is a major technological advance that the SKA has initiated here in Africa, in South Africa. MeerKAT and then the SKA even more will produce 3-dimensional maps of galaxies that I've been talking about that allow us to probe the dark sector of the universe. And here is a computer simulation of the kind of hydrogen emission we might see with the color scheme here just encoding the intensity of the emission. I'm afraid I can't go into more details about that because of time, and I'll just end off by saying something about the other science. It's not just the dark universe that I've been talking about, but there are many other science cases that the SKA will be tackling, just as important as the ones that I've been talking about. For example, the SKA will detect a huge number of pulsars, mainly in our own galaxy, and these things not only will lead to greater understanding about the nuclear and particle physics of neutron stars, but they will also lead to an indirect detection of gravitational waves at different frequencies from those detected by LIGO and Virgo and their upgrades. We'll also be able to probe the supermassive galaxies, supermassive black holes that exist at the center of most galaxies, and which are shrouded in dust and therefore very difficult to probe with optical telescopes, but the radio waves go straight through the dust, and so the radio telescope is an ideal thing to probe these supermassive black holes, trying to understand how they emerged and what role they play in the formation of galaxies. I already mentioned scanning the cosmic dawn. It's when the first stars form, that'll be the epoch of reionization, the part of the array in Australia. Searching for life in our galaxy, that's another big thing which I don't know much about, but obviously very interesting. And then, of course, finally in SK Phase 2, probing the dark ages before the first stars formed. So I'll end off just by emphasizing the importance of the SKA, and particle physicists in Africa would appreciate this, that the building of experiments in Africa does a huge amount to advance the cause of science, not just in that particular technical area, but beyond as well. Science in Africa as elsewhere, but particularly in Africa because of its level of development and the devastation of colonial genocide and Holocaust that happened in Africa. Africa needs more science. It's essential for everyday life. It's the basis on which we can help build a society for everyone. Science is at the basis of modern society in a humane society, to help protect the environment which is being annihilated. To understand our origins and our place in the universe, we need science. To help develop a science-based humanist and internationalist worldview. Science can do all of these things as well as the actual task for the experiment, which is much more narrowly focused, but which is part of this. I think it's useful for all of us as scientists to stand back and see where we fit into the bigger picture. And finally, of course, Africa needs, as a major raw material exporter, in order to move beyond simple export of raw material, a knowledge economy based on science is clearly essential. What are the spin-offs for Africa, the SKA, in science? Well, first of all, of course, world-class science will be produced in Africa. We're not just going to export the data to the advanced countries and then wait for them to do the science. So we're busy training people in Africa, in South Africa, and in the partner countries to be able to actually do science with the SKA as well as help build the instrument. It will be a massive boost for science in general, and particularly through big data. The SKA will generate more data than any other experiment before it. The data rates are so huge, I can't actually remember what the numbers are. But current and for the foreseeable future, it's impossible to store this level of data, and it's impossible to mine it with current techniques and software. But that kind of challenge is going to spur the computer scientists and the data scientists to actually make those advances and the technologists to make the advance in storage. So it's going to have huge spin-offs for big data science which go well beyond astronomy into many other areas. It will raise the profile of science, especially amongst the younger generation. You might think science is a good career. We hope so. We need more young people to come into science. And of course, there's spin-offs for local industry and infrastructure. And this SKA observatory is going to be around for at least 50 years, hopefully longer. It's not just a one-off experiment which becomes obsolete. It is an observatory, an international observatory. And I'll end off just by another little, taking even a bigger picture. Science belongs to humanity, and it relates also to the past of the country where this SKA is being built, SKA Madhya in South Africa. it's possible that science actually began in southern Africa. This here is in the Blombos Cave in southern Africa, the southern part of South Africa. This is the oldest evidence of abstract thought yet found. Isn't that amazing? It's well over 100,000 years old. And hunter-gatherers, the origin of humans is currently thought to be in southern Africa, on the coastal region not far from here, all around here. Those hunter-gatherers of those times obviously wondered at the night sky, and that was, in fact, the foundation of astronomy, which itself was the foundation of science. So there's a nice connection. 200,000 years later, there we are, MeerKAT, same night sky. 200,000 years is just a blink of an eye for the universe. And I'll end there.